Well, good morning and welcome to the Boston summer. It's going to be worse. So, we talk about engines. Come on, I turn you off. And we discussed that in order for an engine to work in cycles, it has to operate between two different temperatures because it needs to gain some energy in order to produce some work, but also it has to release some energy in order to be brought back to the original state. And here I have a model. Let's hope it's going to work when it's very hot and humid. Everything is affected by humidity. So, good. So I just boiled some water, and this is so-called Stirling engine. And this is liquid nitrogen, very cold one. And I'm going to place exactly similar model on this one. Now let's wait and see if anything going to happen eventually. And I got a question for you while we wait about any engine. You have to make an announcement.
Okay.
Try it. I don't know.
Testing. Ooh, it does. Hi, everyone. My name is Kat, and I work at a lab called the STEP Lab. I'm recruiting for a study for my paper and for my coworkers' papers, and also for my senior thesis. That's boring to you all, so I guess I'm going to get to the point that we pay $20 an hour for our studies, and there are a number of studies to do. So if you're interested, which I know you all are, please take a flyer that's at the front of the class.
Thank you. All right, this one is already working. This one is getting there. Hopefully it will eventually. Maybe it's broken. Maybe it needs a jump start. Oh, it has too much friction. I can hear it. Well, we'll see. So, the question is about the change in the internal energy for the complete cycle. And the cycle is called the cycle because it starts and begins at the same state. And it doesn't really matter how complicated the cycle is. Eventually, no matter what process is being used, and there are many different processes, it's supposed to come to the initial state. An initial state and a final state in this situation should have exactly the same temperature, which means the internal energy shouldn't change with the whole cycle. For one process, it might increase. For another process, it might decrease. But over the whole cycle, All right, I don't have to touch it anymore in order to spin. So yeah, too much friction in this guy. Probably someone just dropped it. That's what happens with the equipment usually. People borrow it, drop it, bring back, and say nothing. That's it. So this example demonstrates that the same medium might at the same time be provider of a heat or a heat sink, so-called, a medium which takes away the heat from the system. In this situation, when I poured hot water, the hot water is the source of the energy. But where does it go? Well, the air. The air has a lower temperature. Room temperature is below 100 Celsius. So the air now represents the heat sink, and the hot water represents the heat provider. In this situation, the nitrogen is cold, and the air in the room is warm. And that means the same air which takes away energy here produces energy there. And, well, as long as there is temperature difference, the engine might operate with different efficiency, different amount of work. Getting there is done for different engines. But again, it doesn't matter what we use, what specific material or substance do we use for providing temperature difference. What matters is the existence of temperature difference. And you can see actually they spin in opposite directions. It's the same engine, but here it spins for you clockwise and here counterclockwise, because the temperature difference is opposite here. Here we have hot, cold, and here we have cold, hot. Well, anyway, let's see how long they last. The next, of course, question would be about work. That's what we want to use from the engine. So we pump energy in to produce some work. The work is done, some energy taken back, and over the whole cycle, there has to be some net work done by the gas on a wheel, for example, on anything. And here we have two very similar cycles. The one on the left begins from state number 1, then goes to state number 2, 3, 4, and to state number 1 again. And this arrow represents the direction of the cycle, and that direction has a name, clockwise, so we call it a clockwise cycle. And on the right, we have the same set of states, but we go through those states in opposite direction, and we call it counterclockwise cycle. And let's see what you say about the work done. Question number 3. Well, we've got some distribution. Well, we know in general how to calculate or estimate the work done by a gas. We just need to look at the PV diagram, and for any process, any specific process, the amount of work done is equal to the magnitude of this area between the horizontal axis and the graph. Magnitude means this value could be positive or negative. And when is it positive, when is it negative? When? Well, it depends on what's happening to the volume. When the volume increases, the system expands, the work has to be done by the system is positive. And when the volume decreases, the system contracts, the work done by the system is negative. And here we have several processes. For this process, there is no work. That's an isochotic process, 3, 4, 0. For this process, we do some work. That work will be equal to the area of this red shape, but it also 4 to 1. It also has to be negative because the volume decreases. Now here we have some work done, and the work done for this process from 1 to 2 also is negative because the volume also decreases. Now there is a work done during process 2 to 3, 2 to 3, and for this process the volume increases and the work done is positive. So total work over the cycle, we call it total, we call it cycle, or just W, has to be equal to the sum of 4 numbers. And well, we can see that if we add them up all together, the result has to be, let's check one more time. Now you have to use your ability to relate areas of different shapes and see, oops. So we have a winning answer, which is number 1, which is positive, which is wrong. So democracy doesn't work in physics. Rules work. So you can see that what we should write mathematically is negative area for process 1,4, negative area for process for 1,4 or 1. Okay, would be absolutely accurate. For 1, 1, 2, and well, plus positive area for process 2, 3. Together should be negative, just from the picture. The easiest way, of course, to see it is to pick a very simple cycle like this, for example. And direct it in a way you like. Well, in my example, I have it directed counterclockwise. So, and we can see immediately that there is more negative work done during the contraction of a system than positive work done during the expansion of the system. So all overall work is supposed to be negative. And of course, now we just have to kind of remember the rule. When work is positive, when work is negative, could have been same cycle, but direction matters. But the more important fact that the magnitude of this work done in one cycle will be equal to just area of this shaded shape. The magnitude is equal to the area inside the cycle. That's it, which makes our calculations easier. Now, for each cycle, doesn't matter how it looks like, simple cycle, complicated cycle, doesn't matter. For each cycle, we can talk about heat, internal energy change, work done per each process or per cycle altogether. And we've done some calculations per individual processes. So for example, let's pick up, I don't know, process like this, just to review. Process like this from 2 to 3. So what should we say about it? Well, first of all, we can see that the volume decreases, hence work will be negative. But this process, if we just relate, like P2V2 should be equal to nRT2, and on another hand, P3V3 should be equal to nRT3, because both values, pressure and volume, for the second state are greater than pressure and volume for the third state. That immediately tells us that temperature of the second state will be higher than temperature of the third state. And if temperature drops, the change in the internal energy will be negative. Temperature drops, change is negative. And for example, now for this particular process, if we add the change in internal energy and work, two negative numbers, Q will be negative, which means during this process, this system releases the heat. Well, what about the whole cycle? Well, that's actually much more easier and more useful for us because we talk about engines. For the whole cycle, we just said there is no change in the internal energy because for the whole cycle, initial temperature and final temperature are same. And for the whole cycle now, if we apply the first law of thermodynamics, turns out this amount of heat will be equal to the work done. But we just said that for some processes, this heat for a specific process, this heat might be negative. And for another specific process, for example, Q23 is negative, Q12 will be definitely positive. So this total amount of heat can be broken down into two individual parts. Absorbed, released. An absorbed heat, of course, is positive, but the released amount of heat is negative, so we can explicitly show it mathematically as -1 times the absolute value of it. So it turns out this is how we always can relate the amount of heat system absorbs, the amount of heat system releases, and the total work done in one cycle. And first of all, what we can see from this expression is that the amount of work is always less than the amount of heat system absorbs. It's impossible to turn whole absorbed heat into the work. Some amount always get lost. So here I have readable version, and now let's just calculate for a specific situation the amount of heat absorbed, the amount of heat released, compare the numbers. All right, these guys. Now this is water. I cannot do anything about it but just pour back into a sink. This is liquid nitrogen. That's it. This is how they clean the floor. It evaporates immediately and collects all the dirt. Well, so a specific problem. A certain amount of heat. Oh, I skipped this problem yesterday, so I want to use this as an example related to cycles. First, we talk about a specific process, and then about a cycle. So a certain amount of heat is transferred to a system, so it is absorbing this heat. And the pressure remains constant, and the volume changes, so technically nothing really new. So let's do it more or less quickly. So first, what do we know? Heat, the pressure, the initial volume, the final volume, and the number of moles. Well, it is always helpful to sketch a PV diagram, and in this situation, it's a standard diagram for isobaric process. And actually, even we didn't ask, we can calculate the work, right? Because we know pressure, we know initial volume, final volume. So the work will be equal to P times delta V, which is 2,000 kilopascals times 80 liters minus 40 liters, which will be equal to 2,000 times 40, 8, 1, 2, 3, 4 zeros joules. Now, we need to calculate the change in the internal energy. And we have two options. One relates internal energy and temperature. Second relates internal energy and, in this particular case, work. So I times 80,000 over 2. Well, the issue is we don't know what type of the gas is it. Monatomic, diatomic, polyatomic. So I could be equal to 3 or 5 or 6, and we don't know that. So what do? We always have the same options. The option number 1, giving up. The option number 2, well, looking for the variable which we don't know, but we need. And if we choose the option number 2, we start searching for additional connections. For example, what variable hasn't been used yet? Q, heat. And again, there are two relationships for Q. Well, my guess would have been using the last one, because we already have something about work and change in internal energy. So Q equals, this is my choice, my hypothesis. I write the first law of thermodynamics. Now I know this number, kilojoules. And I know it has to be equal to I times 40,000 plus 80,000. Well, it gives me an equation with only one unknown. So plus I can cancel for zeros immediately. So what's left? 32 minus 8 over 4 equals I. I equals 6. This is a very, very rare, unusual situation when we need to find the number degrees of freedom. But again, it doesn't matter what are we looking for or what we know. The strategy matters, and the strategy means connecting information, and we did it. Well, we have to finish now the calculation. For example, now we can calculate delta U. It will be equal to 6 times this, which is 1, 2, 3, 4 joules. And of course, we're done. If we add these numbers, work, and change internal energy, we of course get the original number of heat. Well, so that was a review. Now we have to apply this reasoning to a cycle. So we are adding 2 more processes. And what we know about those processes, pressure, okay, and 1 more pressure. So this is what we know from the previous calculation. The Q equals this amount of kilojoules, and the work done for this process is equal to 80,000, right? Okay. And what do we need to calculate? Well, everything basically for the whole cycle. All right. Let's calculate work for the whole cycle. Well, first of all, actually, stop. Let's calculate the change in the internal energy for the whole cycle. And the number is 0. For the whole cycle, there is no change. For the whole cycle, the amount of heat equals work and equals to the area inside this shape. In that's the area of a triangle. So how do we calculate the area of this triangle? 1/2 height times base. 1/2. So I can write P1 minus P3 times V2 minus V1. That's geometry. Has nothing to do to physics. Now we can use numbers. 1/2. Difference. (2,000 minus 1,000), 1,000 kilopascals times difference 80 minus 40, 40 liters. So that gives me 4 over 2, 2, 1, and 4 zeros. 1, 2, 3, 4 joules. Well, okay, let's do it. Process 223. We know the heat is supposed to be negative. Let's calculate it. So this amount of heat should be equal to the change in the internal energy plus the work done during this process. So let's do it step by step. The work, that's easier to do because we just have to calculate the area of this trapezoid. So if you do it at home, you can draw this picture on a piece of paper and then turn it by 90 degrees. So the trapezoid would look like you used to see it in the math class. So you need to see the height and two bases. And the expression is equal to 1/2 times height. And the height here is the difference between two volumes. So it's going to be V2 minus V3 times the bases. And each base of this shape is equal to a given pressure. Well, let's write it, okay. P3 plus P2 technically. So now we can use numbers. The difference, so 80 minus 40, again 40 liters. And here, that's supposed to be 1,000 plus 2,000. Now, there's one more thing which is missing here, which is what? Technically, I have to grab my coffee, walk around. What is missing in this calculation? Yes? Yes, I have to add a minus. I'm calculating area, but then I multiply by +1 or -1, depending on what's happening to the volume. Or, yeah, you could use difference, literal different change in the volume, final minus initial. So we know the work has to be negative. We said it several times. Now we have to finish our calculation. That's going to be -20 times 3,000 and then -6 and 4 zeros, joules. Now, delta U23. We know, yes? Oh, this is the math question. This is the trapezoid. This equals 40 liters. This equals 1,000 kilopascals. And this equals, from here to here, the long base, 2,000 kilopascals. Technically, I shouldn't be answering this question. It's a math question. I'm a physics teacher. So it's a combination of geometry. You shouldn't do it only this way. You could have broken down this whole trapezoid into two pieces, a triangle and a rectangle, and add them. This is how in geometry the area of a trapezoid is derived. And again, it's helpful to look at it in a way we used to look at a trapezoid in the math class. And that's it. I don't know, it's just all in shape. Now, this should be equal to 6/2 because we know that the number of degrees of freedom is 6 times well, let's do it once. P3 V3 minus P2 V2. This equation has been on a slide a couple of times before. We just never used it so far. What does it come from? It comes from the equation for internal energy, I over 2 nRT, which can be written as I over 2 pressure times volume. And that's it. We just used it twice for calculating literally difference between two numbers. One number represents the energy at the third state. Second number represents the energy at the second state. And, well, 6 over 2, 1,000 times 40 minus 2,000 times 80. And that's going to be negative number, and that's going to be 3 times 1,000, and that's going to be 40 minus 160, so 120. 1,000, 2 times 8, 16, 160, 120. So that's going to be negative 360000 joules. In all problems related to gas law or first law of thermodynamics, we always have more approaches than one. We could have done it differently. We could have used temperature, because we also can calculate each temperature. If we want to, we can calculate temperature number 3, because the ideal gas law says P3 should be equal to nRT3. And calculate temperature, and calculate temperature number 2, P2 V2 equals nRT2, and calculate temperature difference. So there's always more equation than one. Well, and the easiest way now, for example, if we want to in this particular problem, we can follow the we can follow all the steps for the third process, but we know that if we add Q1, Q2, and Q3, we should get the total amount, which is known. So, well, and again, the work done in one cycle equals 20,000 joules, but the amount of heat it absorbs equals 32,000 joules. No, 320,000 joules. So it takes a lot of heat but does a little of work. To describe this property of an engine, we use a new quantity. We call it efficiency. An efficiency of a cycle, by definition, is equal to this ratio, the amount of work done in one cycle over the amount of heat absorbed in one cycle. And it's never equal to 1 or 100%. This equation tells how to calculate efficiency in absolute values in the International System of Units. But if you take this number and multiply by 100%, that is also efficiency, but percent is not international unit. It's like degrees. Yeah? Convenient, but doesn't belong to International System of Units. Yeah. Now, so in this particular situation, if we want to calculate efficiency, we just have to divide two numbers. So we know, oh, actually, we didn't know yet. We know the work. Sorry, the work was 20,000, correct, joules? And this should be the amount of heat absorbed. We know this number, heat 1, 2, Was it 80? Yes. No. That was 320. That was not total. So I have to finish my third process. It was not total. This was only for this process. And for this process, 2, 3, that was a negative number, which was equal to, where is it? Which was equal to negative 60,000 and negative 36. So negative 60, negative 36, 1, 2, 3, 4 joules. So 1, 2, 3, 4, 1, 2, 3, 4, 42. Yes, 1, 2, 3, 4 joules. 1, 2, 3, 4, 1, 2, 3, 4. Okay. How can I calculate the amount of heat? Well, we actually can do it differently. We don't have to, again, walk through the third process. We know that this amount of heat minus 42,000 should be equal to the work. That's just the first law of thermodynamics. So we can calculate this amount of heat using the first law of thermodynamics for so many zeros. 1, 2, 3, 4. So 1, 2, 3, 4. So 4, 4, 0, 0, 0, 0 joules. And now we can finish calculating efficiency. It will be a very, very inefficient cycle. 2 over 44. 1, 2, 3, 4. Normally people do multiply by 100%. So 0, 0, 0, 0, 0, 0, 0, 0, 200 over 44%. .5, which was basically an efficiency of first steam engines. Well, so these are the commonly known processes: constant pressure, constant volume, constant temperature. However, there is one more important process. We call it adiabatic process. By definition, this is a process which is happening without heat exchange with the surrounding. How can it happen? Well, option number one, we can insulate the system from the surrounding, so the heat exchange only happening inside. Thermal equilibrium is reached, we know what to do about it. But there is another option which is very practical. When the process happening is so quickly, so fast, that there is no time for the heat exchange with anything outside of the system. So if that is happening, Q equals 0, no heat getting absorbed or released. In that situation, the change in the internal energy is related to the work done by the system or on the system. So if we do a positive work on the system, the internal energy increases, which means temperature increases. And if we do a negative work, for example, expand, the temperature drops. All we have to do is just do it fast. So let's see some examples of the adiabatic process, and let's hope they work, because for the first experiment I have to use a special type of paper which has very low temperature of ignition, flammable paper, but if it's getting moist, that's it. So I have a piece of flammable paper, and I want to put it inside a cylinder. Now a piston goes in, and if I move it slowly, nothing happening. Now let's see if anything happens if I try to move it very, very quickly. So what happened? Because I did it very quickly, the temperature jumped to the temperature above the temperature of ignition for this paper, and that is how the diesel engine actually works, based on this principle. So what is happening if instead of quickly decreasing the volume, we will be increasing? In that case, temperature should drop. And, well, let's try to measure it. So I have a standard CO2 cartridge here. And if I pinch it, the gas, carbon dioxide, should leave it very, very quickly. So it's going to be very fast expansion. The temperature should drop. To measure temperature, I have to bring this object into the contact with the thermostat. So I have to hold them together. So now it shows the room temperature about 26 Celsius. Now I have to be very careful because of two reasons. First of all, people have been pinching the fingers if they don't do it right. Secondly, when the gas starts flying out, it becomes a bullet because of the Newton's third law. That's why I need to have a holder. See? It even drops to negative values. So when the gas expands so quickly, the temperature drops significantly. And there is a special device which people use to make snow. Hopefully it's going to make snow. Why? Again, when we release it, that's actually same CO2 cartridge, basically, just big one. So when it's getting released, the temperature drops, and it drops below the freezing temperature of water, so droplets of water get frozen, and that's why we see snow. That's how the God makes snow. He has a lot of, or she, we don't know, a lot of fire extinguishers. Yeah, and angels who help. That all makes sense now, right? Well, why this particular process is important? We don't need to know how to relate pressure, temperature, volume for this process. We just need to know it's a special process, because if we use that process, we can construct an engine which operates at the maximum possible efficiency between two limited temperatures. So for any engine which operates between two temperatures, we may create many, many different cycles, and they will release energy differently, absorb energy differently, so efficiency will be different. But there is a special cycle which is composed of two isothermal processes and two adiabatic processes, which results in the maximum possible efficiency for an engine operating between two temperatures. The high temperature we call hot temperature, and the low temperature we call cold temperature. And the equation on the top describes how to calculate efficiency for any engine. And this equation in the middle tells us how to calculate the efficiency for an ideal, for the best possible engine. And of course, if we use an ideal engine, we can use these equations together. For example, there is a cycle in an ideal engine, and we need to calculate the hot temperature. Well, all right, we know what to do. Because of this word, we can write the expression for the maximum efficiency in temperatures. But because it is an engine, we also can write standard definition for any efficiency. Now, the tricky part is not using Celsius, because the expression for the ideal efficiency assumes absolute temperature measured in kelvins. So first we have to convert Celsius into kelvins. $300, very convenient. Now we can start using numbers. What do we know? First of all, we know also every cycle does work. This is the amount of work it does in one cycle. And releasing, so that's what we call released, called Q, 600 kilojoules. And now we know that if we add these together, that will give us the amount of heat the engine absorbs. Zero, 201 joules. Now we can write an equation. That's what we're looking for, minus that's what we know, over the same unknown, should be equal to the work, which is 420,000, over the amount of heat absorbed, 102. 0, 0, 0. Well, I will let you to finish it at home. This is mathematical equation with one unknown. We have to rearrange the numbers and calculate it. The answer will be in Kelvin, and you may need to convert it back to Celsius. Questions? All right, so this is the summary of this topic. Now, please tell me, what do you think about this question? So what I have here is a jar. Maybe I should show it once. This jar has layers of balls: yellow, red, white, green, blue. I can move it to the left, I can move it to the right. Nothing changes. This is a process. But in the question, you should answer what will happen if first I make it turn 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now I'm going to make 10 turns backwards do you expect that after doing turns in the opposite direction, I will see the layers again? 1, 2, 3, 4, 5, 6, 7. I have to do it. It's physics. 9. No layers. So after making 10 turns, I made it chaotic. And it remains chaotic even if I try to move it back. And mechanics, which is described by Newton's first, second, third, fourth law of conservation of mechanical energy. It is described by law of conservation of linear momentum. Mechanics cannot explain why it remains chaotic. From a mechanical point of view, everything is reversible. We could, record it, and on recording, that chaotic system would become back the ordered system. But that's what is happening in the real life. And none of the existing laws can explain that, which means there has to be a different law. And the different law, which has a name, second law of thermodynamics, tells that a system, any system on its own, always either remains in the original state or the chaos in the system increases. On its own, a system never can be moved from a chaotic to more ordered state. Of course, we can repair the order, but in that case, we would have to do that. We would have to open it, pour it down, and then use our hands to put the balls back in a specific order. But only people can make order, basically, in the whole universe. Well, maybe aliens as well, but we don't know yet. So without interaction with intelligent species, the order in the whole universe only decreases. Disorder, chaos, only increases. That's basically the statement which second law of thermodynamics tells. And this experiment separates process into different groups. One we call reversible, second we call irreversible. A reversible process is a mechanical process, like motion, left and right. But normal thermodynamical processes are irreversible. If my electric kettle is sitting on a bench, it only gets colder, it never gets hotter. Theoretically, in mechanics, nothing prevents molecules inside from starting moving faster, but it would require getting energy from the outside, but that is not happening. Why? Well, we have to say because there is law which forbids this from happening. That law has a name, second law of thermodynamics. And of course, there is a special variable which describes that. We call it entropy, and entropy is just measure of chaos. And we say entropy can only increase on its own. Only we, intelligent species, can decrease entropy, can bring more order. That's our mission. That's why we have been created, to bring the order to the universe. Well, that's the statement. In the uninsulated system, the entropy only increases, chaos only increases, and only the second law of thermodynamics can explain why, by turning the jar back, we cannot bring it back to the ordered state. So the answer to this question would be second law of thermodynamics. That's what prevents a standard thermodynamical system to go from disordered state into the ordered state. Learning is also a reversible process. And not because what we learn stays for us forever. No. Most commonly, what we learn, eventually we forget. But learning changes the structure of the brain, because the brain is basically a thinking muscle. So if you have a dumbbell and you exercise your right hand every morning, you know your muscle changes. It grows, it's getting more solidified. Yeah. Same processes actually happening in the brain. But there's an interesting analogy. For example, if for 1 month you're doing this, and you forget doing the same exercise with your left hand, and in a month you're surprised, why is my left hand so weak? Well, the answer is you didn't exercise your left hand. So if you're exercising your brain using exactly the same exercise, like memorizing and nothing else, that same process happening in the brain, only one function getting exercised, only one function getting developed. So when you read in a paper why our high school graduates can't, for example, reason, because no one taught them how to reason. They've been taught how to memorize. That's it. It's all about how people being taught. We've learned everything. Last question. Well, you don't need to see it's on the screen because the copy is on a website. Now, you did your evaluation yesterday, but, well, I would probably say no more than 4 people would ever read. Maybe a department chair, maybe someone at the summer term. I read it. That's it. So if you feel like you want to share your experience with the wider audience, go online. But if you do that, saying, oh, I loved it or I hated it, doesn't help anybody because it's just venting out your emotions, which is good for you. But if you really want to say something, be specific. List things which you didn't like or things which you like giving an advice. If you want to take this particular course, be prepared for, and then, I don't know, whatever you list, And we are officially done. Now it's your turn. Yes? Same? Yes. I will probably send an email again. Yes?
Other than the formula sheet, what else will be provided to us? For instance, do we need to memorize the I values for the monatomic gas, whatever it is? And will we need to
Can you tell me, for the diatomic gas, what I is equal to? You don't have to know, it will be provided.
Atmospheric pressure as well? Value of atmospheric pressure as well?
If it will be needed, yes. All constants, You're asking specific questions. The general question is, will be constants provided? Yes, all constants will be provided. That's it. You don't have to memorize constants. Yes. If you have no questions, you're free to leave this room. Yes.
On the question, sorry, on the equation sheet, it says QH and QC. Is QH just the heat in
Yes.
the system and QC is
Out.
out of the system?
Yes. It's same, like absorbed and released, in and out. It's like there are different terms, more scientific, less scientific, like slang, but they mean the same thing. Yeah. QH is heat going into the system. Some work is done, and a part of heat goes out. The only thing is, normally people don't use vertical bars when they write equation like this. And if they forget that it represents absolute value, they might make a mistake with the pluses and the minuses, and that's it. Yes? Have a question? Not yet. I have to stay here until there is at least one student remains in this room, or it's 10 a.m. So I'm staying. You're free to go. Yes. No. I sent an email yesterday which says if you have any questions about your participation grade, you have to address those questions in person on Thursday or Friday. That's a time window, and that's a procedure process. That's it.
Okay, so we're talking about monatomic gas, and that basically the work that is being done through the system is this.
I can't answer your personal questions. You have to ask for the whole class. You can use the microphone.
Really?
Yes, it's a class time. My office hours begin today at 11:30, I think.
Okay, so we're asked to find the Q
This is homework
for number
homework 3, part 4, number 3, right?
Yeah.
Okay.
Okay, so it's asking to find Q, and it says that the work done on the system is
On the system.
303 joules.
So first of all, this is a tricky part. I'm not sure if you used the fact that the work done by the system should be equal to negative.
Okay, but then, so then we have to find the change in the internal energy, right?
So you start from application of the first law of thermodynamics, and this expression implies we're using the work done by the system.
Okay.
And you know this number, right? So, and do you know Q, or you have to find?
No, we're solving for Q.
So you need to know now the change in the internal energy. And
Right.
We have two options for that. Well, technical delta, I don't know what process is there. So where else do we know?
We know the temperature change, so we're going to use the other one, and we know the number of moles.
What number of moles?
8.8.
What temperature change?
Final is 145 Celsius, and initial is 22 Celsius.
145 minus 22.
So do we use, so my question is, do we use Celsius or do we use Kelvins for this?
Do you know I?
I is going to be 3, right? Because it's monatomic?
Yes. So the equation which relates Kelvins and Celsius looks like this.
Yeah.
So if you have two temperatures, and then you need to calculate the difference.
Mm-hmm. Okay, so we do use Kelvins.
These constants getting cancelled. So when you're calculating temperature change, there's no difference between using Celsius and Kelvins.
Okay, let me see if it works. 'Cause it wasn't working before.
It's supposed to, I saw people done it. The only tricky part was
Yeah.
a minus. Good morning. Yeah, thanks. Yes.
This is homework 1, I think. Yeah, homework 1.
Well, that's homework 3.
Yeah, homework 3, 1, number 7.
Part 1, number 7. This is about,
Max acceleration, max velocity.
okay, so this is about simple harmonic motion, right?
Yep.
So, first of all, it's very useful just to remember that for any simple harmonic motion, we always can sketch a graph for position as a function of time like this. And it doesn't matter how it starts. What we know is when the object reaches maximum displacement, x equals amplitude, it stops. So here, velocity equals 0. But here, force and acceleration also reach maximum. And here, another important instant. X equals 0, acceleration equals 0, force equals 0, but speed now reaches maximum value. Always. No matter what, well, of course, it travels back and forth. So if it goes through equilibrium, so there's a spring. If this is equilibrium, at equilibrium, the spring is not contracted, not stretched, so force 0. If force is 0, hence acceleration is 0. But if it reaches, for example, the longest possible displacement from equilibrium, it stops always. So velocity will be equal 0, but it will be, the stretch will be the maximum. And the force, which is k times x, will be at its maximum. Hence acceleration, which is k, well, k over m or omega squared, if I use magnitude, will be at its maximum.
Okay. Thanks a lot.
Yes?
No, I had the same question because I
Okay.
was wondering because of the point, which point it actually changed. It was the velocity maximum. Because at the end, after you find t, you got to divide by 4, right?
Well,
Because at that point.
when we start measuring time, we can measure it from any instant. For example, if we measure from the maximum stretch, this period should be, well, this time interval should be equal to a quarter of a period. And then from here to here, another quarter of a period. And another quarter, and finally another quarter. And that completes a period.
I also have a question of how, like, sometimes I'm confused when you use the negative k in the equation. Because sometimes a lot of...
We used it only once for deriving an equation.
Okay.
Because if we want to write the Newton's second law very accurately, we have to see that, for example, when x is positive, force points to the left, which means it has a negative component. So how do we relate it? Well, if we write it like this, it will be wrong because we're multiplying two positive numbers that should be a positive. So mathematical description of the relationship between the force and the position looks like this. But when we need to calculate something, we just use magnitudes. It's easier. This is what we used to relate acceleration and position, because the same force should be equal to m times a. So if we combine these equations, ma equals this, and acceleration, which is the x component of the acceleration, will be equal to this. And that's it. We used this fact to sketch two graphs. If we know the graph for x, the graph for acceleration is just same shape flipped because of the minus. Why? Because of the minus. Why? Because the force points opposite to location, kind of.
Okay, got it. Thank you.
Sure. Questions? Anybody? Yes?
So, for the simple harmonic motion, that's the only part where our calculator should be in radians?
I don't understand the question, but I will answer it.
Okay.
For the simple harmonic motion, we have several expressions. This is, by the way, also equals, which involve the variable which we call angular frequency. The angular frequency has a unit, radians per second. And if you're calculating maximum speed or maximum acceleration, you must use radians.
Okay.
But if you're calculating cosine of something, whatever number you have here depends on you. You can make it radians, you can make it degrees. I would say, I don't know, if you're not sure, make it radians all the time. But in that case, if you use radians, you also have to know that your calculator also uses radians, or your number will be wrong.
Okay, thank you.
Sure. Yes?
I have two questions. So for this one, it's talking about the Antarctica being covered by the glacial ice. So then this one asks to find the increase of sea level. So just how do you kind of...
What is it happening? Suppose that the volume of glacial ice melts. We have a different question.
I do.
You said you have two questions.
I do, yeah.
This is technically not related to anything
Okay.
we'll learn.
Then never mind. So what is the change of internal energy?
Okay, for the cycle.
Yeah.
The general idea is always the same. We're connecting variables, but the specific process depends on the specific information we know. So your cycle is rectangular, right?
Yes.
So it has 4 processes. And what do we know for each?
We know P naught, B naught.
Can I see it?
Sure.
Thank you. Do you like Mac?
I do.
Assume that this product is equal to 1,000 joules. And this is monatomic gas, I see, because of this. 3/2 means it's monatomic gas. Yeah. Now, what is the work done? This is what you see. You see these variables. 5, this is P naught, and this is 3. Okay, thank you.
Asking
So,
the change of internal energy for each stage of the cycle.
column 1, 2, 3, 4. So 1, 2, for example. Hence, I equals 3. And delta U will be equal to I over 2 N R delta T. But in this situation, because pressure remains constant, I over 2 P delta V. Questions about this? Because if you see this, that's it. That's your first calculation. That's going to be 3/2, 3 P naught. That's how they call it. Times 5 minus this will be equal to, so that's going to be 9/2 times 4, and you have this product, which is given to you as 1,000. So 4/2, 18,000.
They tell you right here.
They say that I didn't know that I was 3, but now.
Yes, you didn't know that because I didn't mention this. They just used the fact that for the monatomic gas, this is how we can calculate the specific key to it. This is that number, I.
Oh, okay. So
In our exam, I would just tell you I equals 3,
Okay.
or I equals 5. That's it. Or I equals 6. Yeah. And for example, briefly, 2 to 3. Yeah. What should we do? Again, same equation. I, 2. Well, this is how it is better to write now. Change in this product, but I equals 3. Now the volume remains constant for this process, and it equals to 5 times V naught. But the pressure changes from, yeah, but we need to calculate final minus initial. So final will be the P3.
right.
And that's it. So again, it gives you 3 over 2, 5, 1 minus 3 is negative 2, and you end up having the same product, which is 1,000.
Okay.
Thank you.
Thank you.
Questions?
Mine isn't a physics question, but I didn't get
Yeah.
credit for lab 8, and I have it if you need to see it.
No, I'm fine.
Okay.
Please send me an email. Yeah, someone probably forgot to enter. I can enter your grade.
Thank you.
Sure. Any questions? Last call. All right. Thank you very much. I'll see you tomorrow. Do you think I remember? First of all, office hours begin right now. Someone will be there. Some teaching fellow, and I will replace that guy. I will check when is my time, and I will be there at that time. Tick, 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 tick. Right, so now. No, we go. You can always crash it if you don't like it later.